Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Optical Characterizations Part 1, Fourier Transform Infrared Spectroscopy FTIR from the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First, we will discuss how does an FTIR spectrometer works, along with the explanation about the Michelson interferometer. Secondly, we will discuss about the optical path delay and the ZPD. Then we will discuss about the interferogram. Lastly, an introduction about the FTIR sampling will be discussed in this module. So students, let us start with the basic introduction about the module. FTIR. It stands for Fourier Transform Infrared Spectroscopy, the preferred method of infrared spectroscopy. When IR radiation is passed through a sample, some radiation is absorbed by the sample and some is passed through or transmitted. So the resulting signal at the detector is a spectrum representing a molecular fingerprint of the sample. So the usefulness of the infrared spectroscopy arises because different chemical structures, molecules produces different spectral fingerprints. FTIR spectroscopy is a technique that uses infrared light to observe the properties of a solid, liquid or gas. It is used in many different applications to measure the absorption, emission and photoconductivity of matter by shining a narrow beam of infrared light at the matter in various wavelengths and detecting how the matter responds to each wavelength. So once the data has been obtained, it is converted into digital information using the mathematical algorithm known as Fourier transform. So the goal of any absorption spectroscopy, FTIR, UV visible spectroscopy, etc., is to measure how well a sample absorbs the light at each wavelength. The most straightforward way to do this is the dispersive spectroscopy technique, is to shine a monochromatic light beam at a sample and measures how much of the light is absorbed and repeat for each different wavelength. This is how some UV visible spectrophotometers work, for example. FTIR is a less intuitive way to obtain the same information. So rather than shining a monochromatic beam of light at the sample, this technique shines a beam containing many frequencies of light at once and measures how much of the beam is absorbed by the sample. Next, the beam is modified to contain a different combination of frequencies, giving a second data point. This process is repeated many times. So afterwards, a computer takes all this data and works backward to infer what the absorption is at each wavelength. Let us now discuss how does the FTIR spectrometer works. So before that, first we'll discuss about the Michelson interferometer. The FTIR is typically based on Michelson interferometer experimental setup. An example is shown in this figure. The interferometer consists of a beam splitter, a fixed mirror, and a mirror that translates back and forth very precisely. The beam splitter is made up of a special material that transmits half of the radiation striking it and reflects the other half. Radiation from the source strikes the beam splitter and separates it into two beams. One beam is transmitted through the beam splitter to the fixed mirror, and the second is reflected off the beam splitter to the moving mirror. So the fixed and the moving mirrors reflect the radiation back to this beam splitter. So here mirror 1 is the fixed mirror and mirror 2 is the moving mirror. So again, half of this reflected radiation is transmitted and half is reflected at the beam splitter, resulting in one beam passing to the detector and the second back to the source. What are OPD, optical path difference, and ZPD, zero path difference? Optical path difference, OPD, is the optical path difference between the beams traveling through the two arms of an interferometer. OPD is equal to the product of the physical distance traveled by the moving mirror multiplied by 2, 4 or other multipliers, which is a function of the number of reflecting elements used, and n, the index of refraction of the medium filling the interferometer arms, air, nitrogen for purge systems, etc. The raw FTIR data consists of a number of signal OPD pair of values. FTIR has a natural reference point when the moving and the fixed mirrors are the same distance from the beam splitter. This condition is called as the zero path difference or ZPD. So the moving mirror displacement delta is measured from ZPD. So in this figure, the beam reflected from the moving mirror travels 2 delta further than the beam reflected from the fixed mirror. The relationship between the optical path difference and the mirror displacement delta is OPD equal to 2 delta n. So this figure shows the schematic representation of the waves and their phases, input and output, and the two arms of the interferometer as the scan goes from zero path difference condition to OPD equal to lambda, OPD equal to 0 case, lambda by 4 OPD case, lambda by 2 OPD case, 3 lambda by 4 OPD case, and 1 lambda OPD case. The interferogram. Interferogram is the name of the signal format acquired by an FTIR spectrometer. It is usually significantly more complex looking than a single sinusoid, which would be expected if only a single wavelength of light was present. This figure shows the interferogram of a broadband light source. The center burst The big spike in the center of this figure is a telltale signature of a broadband source. Its origin lies in the fact that all wavelengths are in phase at the ZPD. Therefore, their contributions are all at maximum, and a very strong signal is produced by the system's detector. Now, the below figure shows a broadband source interferogram. As the optical path difference OPD grows, different wavelengths produces peak readings at different positions. And for a broadband signal, they never again reach their peaks at the same time. Thus, as you move away from the center burst, the interferogram becomes a complex looking oscillatory signal with decreasing amplitude. So the x-axis of the interferogram represents the optical path difference. Each individual spectral component contributes to this signal. A single sinusoid with a frequency inversely proportional to its wavelength. This leads us to the definition of the unit of spectral measurement. So the wave number centimeter-1 is denoted as n. So a wave number represents the number of full waves of a particular wavelength per centimeter of the length. Typically in vacuum, index of refraction n equal to 1. So the advantage of defining the spectrum in wave numbers is that they're directly related to energy levels. So a spectral feature at 4000 centimeter-1 spectral location represents a transition between two molecular levels separated by twice the energy of a transition with spectral signature at 2000 centimeter-1. FTIR sampling, its introduction. So there are four major sampling techniques in FTIR. Each technique has strengths and weaknesses which motivates their use for special example. So this figure shows the basic light interaction with the sample. And the first one which we are going to discuss is the transmission. In transmission, the infrared radiation is passed through a sample and the transmitted radiation is measured. The spectra obtained will be representative of the whole of the volume sampled and localized. For example, surface properties can quite easily be lost in the bulk properties depending on the size and the nature of the sample. It is only useful for thin, less than 10 micron samples, or when looking at weak bands such as overtones in thicker samples. Often sample preparation such as the manufacture of KBR disc or nodule mull preparation is necessary, which can be time consuming and difficult to reproduce. The other phenomena is the attenuated total reflection, ATR. An attenuated total reflection accessory operates by measuring the changes that occur in a totally internally reflected infrared beam when the beam comes into contact with a sample. This is indicating in this figure. An infrared beam is directed onto an optically dense crystal with a high refractive index at a certain angle. This internal reflectance creates an evanescent wave that extends beyond the surface of the crystal into the sample held in contact with the crystal. It can be easier to think of this evanescent wave as a bubble of infrared that sits on the surface of the crystal. This evanescent wave protrudes only a few microns, 0.5 to 5 microns, beyond the crystal surface and into the sample. Consequently, there must be a good contact between the sample and the crystal surface. In regions of the infrared spectrum, where the sample absorbs energy, the evanescent wave will be attenuated or altered. The attenuated energy from each evanescent wave is passed back to the IR beam, which then exits the opposite end of the crystal and is passed to the detector in the IR spectrometer. So the system generates an infrared spectrum. For the technique to be successful, the following two requirements must be met. Number one, the sample must be in direct contact with the ATR crystal because the evanescent wave or bubble only extends beyond the crystal 0.5 to 5 micron. Second, the refractive index of the crystal must be significantly greater than that of the sample, or else internal reflectance will not occur. The light will be transmitted rather than internally reflected in the crystal. Typically, ATR crystals have refractive index values between 2.38 and 4.01 at 2000 centimeter inverse. So it is safe to assume that the majority of solids and liquids have much lower refractive indices. And the advantages are: ATR is an IR sampling technique that provides excellent quality data in conjunction with the best possible reproducibility of any IR sampling technique. It has revolutionized the IR solid and liquid sampling through faster sampling, improving sample-to-sample reproducibility, minimizing the user-to-user spectral variation. Most importantly, the improved spectral acquisition and reproducibility associated with this technique leads to better quality database building for more precise material verification and identification. So ATR is clearly an extremely robust and reliable technique for quantitative studies involving liquids. Next is the specular reflection. The incident radiation focused onto the sample may be directly reflected by the sample surface, giving rise to specular reflection. And it may also undergo multiple reflections at the sample, resulting in diffuse reflection. In external reflectance techniques, the radiation reflected from a surface is evaluated. So, specular reflection is defined as the light reflected from a smooth surface, such as mirror. Any irregularities in the surface are small compared to lambda at a definite angle. The incident radiation focused onto the sample may be directly reflected by the sample surface, giving rise to specular reflection. And it may also undergo multiple reflections at the sample and resulting in diffuse reflection. In external reflectance techniques, the radiation reflected from a surface is evaluated. So, specular reflectance techniques basically involves a mirror-like reflection from the sample surface that occurs when the reflection angle equals the angle of incident radiation. It is used for samples that are reflective, smooth surface, or attached to a reflective backing. Thus, specular techniques provides a reflectance measurement for reflective materials and a reflection absorption transreflectance measurement for the surface of films deposited on or pressed against the reflected surfaces as shown in this figure. In absorption reflection measurement, one fraction of the radiation is reflected on the upper interface and contributes towards the spectrum via specular reflection. Another part of the radiation penetrates the surface film and is reflected by the reflected surface. Thus, the light passes through the surface layer twice to and from the reflected surface, leading to increase the intensity of the reflectance spectrum as compared to the normal transmission. So the effective path length depends on the angle of incidence. Therefore, for thin films, a grazing angle of incidence as high as 80 to 85 degree from normal incidence should be used. And for thick films, an angle close to normal incidence is applied. So the most common application of this technique are the evaluation of surfaces such as coatings, thin films, contaminated metal surface. So let us now discuss the diffuse reflectance, which is produced by rough surfaces that tends to reflect the light in all the directions. So there are far more occurrences of diffuse reflection than specular reflection in our everyday environment. So students, in diffuse reflectance spectroscopy, the electromagnetic radiation reflected by roughened surfaces, it is collected and then analyzed. When this technique is applied in FTIR regions, it is termed as diffuse reflectance infrared Fourier transform spectroscopy or drifts. IR spectroscopy, which is known as the Kubalka-Munk reflection, which they developed a theory on the radiation transport in scattering media. Now here a light is incident onto a solid sample which may be partly reflected regularly, that is specular reflection, by the sample surface, partly scattered diffusely and partly penetrates into the sample. The latter part may be absorbed within the particles or be diffracted at grain boundaries, giving rise to diffusely scattered light in all the directions. So, diffuse reflectance spectroscopy is associated with the reflected lights which are produced by diffuse scattering as depicted in this figure. Now, since regular reflection distorts the DRS spectra, thus the regular reflection component should be eliminated in diffuse reflectance measurement. So the drift's accessory is designed to eliminate the specularly reflected radiation. Application of diffuse reflectance spectroscopy. Diffuse reflectance technique is used for powders and solid samples which are having rough surface such as paper or cloth. In diffuse reflectance technique, particle size, homogeneity, and packing density of powdered samples play important role on the quality of spectrum. A sample with smaller particle size having narrow size distribution is preferred. Thus, in order to obtain a qualified spectrum, the sample should be ground into smaller size. In this method, the sample can be analyzed either directly in the bulk form or as dispersions in IR transparent matrices such as KBR and KCl. Sometimes a thin film of KBR powder placed on the sample surface to improve the quality of the spectrum. Dilution of the analyte in non-absorbing matrix increases the proportion of diffuse reflectance in the reflected light. So typically, the solid sample is diluted homogeneously to 5 to 10% by weight in KBR. The spectra of diluted samples are similar to those obtained from the pellets when plotted in units such as log of 1 by R, where R is the reflectance, or Kubilka-Munk units. So students, let us summarize what we have learnt in this module. First, we discussed the working of FTIR spectrometer, that is, how does it work, along with the detailed description of Michelson interferometer. Secondly, we discussed about the OPD and ZPD, which are the very important parameters to study FTIR. Then we discussed about the interferogram. Lastly, an introduction about the FTIR sampling was discussed. Thank you.